Hello everyone, my name is Dennis and I'm a STEAM ambassador from Pasadena City College. Today I'm going to present to all of you this workshop titled The Slide Evolve. So let's start. So this is our schedule for today. First, we're going to have a little introduction so you can get to know me and you know what I do at PCC. Then we're going to have a brief discussion about what energy and electricity are and some of their applications. Third, we're going to start with our experiment for today, titled A Voltaic Pile. And lastly, we're going to discuss how chemistry and physics are connected and some of the possible careers that you might choose. Who knows? So, as I said before, my name is Dennis Tercero and I'm a STEAM ambassador at PCC. Currently, I'm studying aerospace engineering and chemistry. I also help tutoring Chem 22, Chem 1A, and Chem 1B. So, you might be thinking, why are you studying two subjects at a time? Isn't one more than enough? Well, that's actually a good question. I started with aerospace because I have always liked the universe and all the mysteries that are waiting to be discovered out there. However, I fell in love with chemistry when I took my first chemistry class at PCC. I realized that actually, you can do a lot of cool things with chemistry, especially because pretty much you are always in the lab, and I really, really like that. This is actually my last year at PCC, and I do hope to transfer to Stanford University, but I'm also going to apply to different schools like UCLA, UC Berkeley, USC, and some more. I want to transfer to a school with an awesome lab like the ones mentioned before. So now you might be wondering, okay, I want to study science for sure, but what is better? Is chemistry better than physics, or is physics better than chemistry? Well, if you were to ask me, I was a chemistry for sure. Well, obviously that was a joke, but yeah, both branches are really cool and important in our world. The answer to this is it depends on what type of scientist you want to be and what kind of labs you want to be part of. In some cases, chemistry is more hands-on than physics because there are many physics problems that involve scenarios that can only happen, for example, inside the stars, black holes, or far, far away universe. So, yeah. But you will learn more about these two branches later in this presentation. Lastly, what would Sir Newton do in this situation? Did you know that Newton invented calculus during the quarantine of 1665? The so-called Black Death or bubonic plague? Really crazy, right? So you might be suffering or you will suffer with calculus because Newton was bored during that quarantine, and the best idea that he had was to create calculus. Obviously, we won't create something that crazy, but I thought it was an interesting fact to share. So, what is the difference between electricity and energy? Shouldn't they be the same thing? Are they equivalent to each other? Sorry, but they are not the same thing. But don't worry, this is a common misconception that some people have. And in some cases, some classes make them seem as if they were the same thing. So let's talk about the differences between these two. A short answer to this would be electricity is a form of energy, and energy is the ability to do work, and that's it. However, we're going to go more in details about that. So, electricity is a phenomenon related to charge. For example, a current is a flow of charge. As such, it is directly related to the charge of fundamental particles, and therefore, a fundamental property. Some fundamental particles that we have are electrons, neutrons, and protons. Electricity is a form of energy. Energy is surprisingly a rather tricky thing to define. It is not really a tangible thing at all. It is a derived property which is conserved and can be transformed into many different forms. For example, kinetic energy is a form of energy which we ascribe to moving objects. Energy can also be separated into primary and secondary energy. So for primary energy, we have petroleum, natural gas, coal, biomass, flowing water, and radiation from the sun. Then for secondary energy, we have many different things that are derived from the ones that I just mentioned before. For example, you have your car, which takes you from point A to B. Obviously, your car needs energy. And in that case, your car is using petroleum or gas, however you call it. That's a form of energy. However, a secondary energy would be, for example, the energy that is stored in your body. Obviously, I mean, you are producing that energy, but that energy comes from something before. For example, if you ate a pizza yesterday, that pizza had many amounts of energy, and that energy came from, for example, the pepperoni is from a cow, the cheese is from milk, and all that stuff. So all those type of energy can be traceable to something before that. So, for example, I have my pizza. Before the pizza, I have my pepperoni. Before that pepperoni, I had a cow. Before that cow, I have grass. Before that grass, I have soil, and like that. So energy comes in several types. We have chemical, we have thermal, we have mechanical, we have electrical, and we have different types of energies. So electricity is in that sense a real thing and properties associated with fundamental charge. Energy, on the other hand, is just accounting, and we are going to go over that later. So let's check some equations to have a better perspective about this. Let's start with the equations related to electricity. So we have those to your left. So we have the first one. So R stands for resistance. We have I current, V voltage, and P power. Here we have only 4 equations that represent different things. Then we have literally tons of equations related to energy. Like, I mean, just think that there are more equations related to energy than the number of slides in this presentation. I mean, it is extremely crazy. At least for me, it's really crazy. The first equation is the photon energy. That's a chemistry equation. The energies of a photon is given by E is equal to H times V, where H is the Planck's constant and V is frequency. Then we have the kinetic energy. So as I said before, that's related to motion of different objects, and that's equal to E is equal to 1 over 2 mv squared, where m is the mass of an object and v is the speed of that object. Lastly, we have the standard Gibbs free energy. One more time, that's chemistry. And that's equal to G naught is equal to delta H naught minus T times delta S naught, where S is the energy available for a chemical reaction to take place. Delta H is the standard enthalpy. T is the temperature. Usually in chemistry, we only talk about Kelvin, so usually that's in Kelvin, sorry. And finally, delta S is the standard entropy. So it is history time. I'm pretty sure that most of you know the name of Thomas Edison, but how many of you know the name of Alessandro Volta? Not many, right? Thomas Edison did invent the light bulb, but he wasn't the only scientist to develop this technology. The journey of the light bulb starts long before Edison patented the light bulb in 1879. In 1800, Alessandro Volta created a voltaic pile, which was a practical way of generating electricity. With an attached copper wire with zinc at either end, the pile conducted electricity. Volta's glowing copper wire is considered the actual earliest manifestation of incandescent lighting. So now you might be wondering, who was Volta? I never heard about him. Well, Volta was an Italian physicist and chemist, and a pioneer of the electricity and power, who also discovered methane. If you're into chemistry, you know about this organic compound. We use this a lot in industry. Some common uses of these are, let's see, to build ceramic tiles, clothes dryers, cooking stoves, water heater, and more. However, be careful with methane. This is a toxic gas in prolonged exposition for humans. And it's extremely flammable, by the way, and it can explode at concentrations between 5% and 15%. But anyway, with the voltaic pile, he debunked the theory that electricity was generated only by living beings, and he's considered the father of electrochemistry. Today, we remember history and those who made history. Volta created a circuit with 2 different metals separated by a piece of cloth or copper soaked in brine, which is an electrolyte. The complete circuit produced an electric current by stacking this element one on top of the other. Volta could adjust the amount of electricity produced to his desired level. This was the first device to provide a reliable source of electricity. A pair of copper and zinc disc with an electroline between them was used by Volta, and today we will be using exactly the same arrangement that he used in 1800. But we will use a different electrolyte. This time we're going to use salt water and vinegar. His achievement ushered in an entirely new branch of science called electrochemistry. But before, let's talk about the physics and chemistry involved behind this experiment. So, what is an electrical cell? So for this part here, we're going to compare the chemistry perspective with the physics perspective. In general, we have two types of electrochemical cells. We have the galvanic cell, and this is pretty much spontaneous redox processes that allow continuous flows of electrons through the conductor where chemical energy is transformed into electrical one. Then we have the electrolytic cell, where the redox reactions are influenced by an external source of current, where the electricity is converted into chemical energy. So that's the main difference. We have energy to chemical energy, and then we have chemical energy to energy. Then we have the physics perspective. In everyday life, we use the word battery. In physics, one battery on its own is called a cell. Two or more cells joined are called a battery. The word battery is used to mean a collection. A collection of cells is called a battery of cells. The cells of a battery are joined in series. I know it's kind of confusing, but that's the definition of physics. So now you know, please study chemistry. So an electrical cell is an electrical power supply. Internally, it converts stored chemical energy into electrical potential energy. So really similar to the electrolytic cell. We have a positive side, which is usually called a cathode, and then we have the negative side, which is usually called anode. We have two types of cells. We have a parallel cell or circuit, and we have a circuit in series. And you can see the diagrams above. So the first one is a parallel, and then we have a series. So it is finally chemistry time. So I know that you want to start with your experiment as soon as possible. I do too, so don't worry. I also want to start this as soon as possible. But now it is time to start doing some real chemistry on a whiteboard. It is time to understand how chemistry works. This is the first step of our experiment. And for that reason, I have a good video explaining how to study and dissect all the parts of a cell from a chemistry perspective. Also, I'm going to explain the physics perspective, but not that into detail, because I believe that, well, at least for our experiment, the chemistry part is way more important. But yeah, so in our case, I will be explaining a copper and zinc cell. So let's go. Hello everyone, so this is the first time that we see each other. It is good to see that you're doing okay during this quarantine. So, I know that it's been a while since the last time that you saw a whiteboard, but take it easy, this is not a math class. Today I'm going to explain how electrochemical cell works. I'm just going to go over the basic principles so you understand how everything works. I'm going to try to dissect all the parts of the cell. And yeah, so I'm going to start with, well, the only one that I'm going to explain is a galvanic cell, which is really similar to what we're going to be doing during our experiment. Obviously, we won't have a galvanic cell, but the principles and all the theory is really similar. So, and once we start with the experiment, you're going to see the similarities. So here we're going to start with zinc and copper. We're going to have a salt solution, which is exactly the same that we're going to do during our experiment. We're going to have salt water, which is basically sodium chloride, and then we're going to have vinegar, which is basically acetic acid. So the first step to try to solve or predict how a galvanic cell works is drawing the actual cell. So let's start with that. So I have here a beaker that is called a container that is called a beaker. So I'm going to call this beaker A. And then I need another beaker or container. So I'm going to call that beaker beaker B. So really original. So I have that, right? Then I need to connect both beakers. And I'm going to use what is called a salt bridge or a U-tube. So this is my U-tube. And I'm going to have a salt solution inside. So this is called a salt bridge. Okay, so next thing is to add the electrodes, which are the pieces of zinc and copper in this case. So these are called electrodes, but you can call them strips. And they are going to be connected with a wire. So this here is a multimeter, and then I need some solution inside the beakers. So obviously I'm not an artist, as you can see, that's why I'm studying chemistry, but you get the idea. So this is a solution here, and I'm gonna call that solution A, and my other solution is gonna be solution B. Okay, so I have solution A and solution B. So now I can start. So the first question that you may have is, okay, so I know that I have zinc and copper. Where do I put the zinc and where do I put the copper? And that's a good question. So we are gonna go over the electrodes. In this case, we have copper and we have zinc. If you don't understand this part here, that's okay. So everything here is gonna be like a little bit hard because this is advanced chemistry, but don't worry, I don't expect you to memorize everything here for our experiment. Our experiment is really easy, and you won't have to deal with calculations or chemistry procedures or something like that, so don't worry, this is just a general explanation. So I have my electrodes, right? I have copper and I have zinc. Then we have something, so we have the salt bridge. So in our case, we're gonna use salt water, and the formula for salt water is sodium chloride. I'm pretty sure that you have seen this before. And then we have vinegar. And this is the formula for vinegar, that is called acetic acid. That's a chemistry name. Okay, and now I'm gonna go over so this is how we abbreviate reactions in chemistry, so RxN. I'm gonna go over type of reactions. So in electrochemical cells, we basically have two types of reactions. So the first type of reaction that we have is a spontaneous reaction. And then we have non-spontaneous reaction. Now the question is, okay, so how do I know if I have a spontaneous reaction and how do I know if I have a non-spontaneous reaction? Okay, so there is a lot of theory behind these terms, but obviously I'm not going to go over that. There is a handy tool to check if you have a spontaneous reaction or if you have a non-spontaneous reaction. So we're going to have a spontaneous, obviously we have two compounds in this case, right? We have copper and we have zinc, or two elements. So I have A and I have B. So I'm going to have A and I'm going to have B. So if I'm going down, I'm going to have a spontaneous reaction. And you're going to understand this in a second. So if I'm going down from compound A to B, I'm going to have a spontaneous reaction. If I'm going up from A to B, I'm going to have a non-spontaneous reaction. So you might be wondering, okay, what is up and what is down? So this is called a standard reduction potential table. I know that is really long, but yeah, that's how things work. So I have two compounds, right? Or elements in this case. So I have copper and I have zinc. So I need to find copper here and I need to find zinc here. So you have to look where is copper and where is zinc to answer this part. So let's start with that. So if you take copper and zinc and then you check your standard reduction table, you're going to see that copper is the first one. You're going to find copper first. So copper 2 plus is going to give me copper metal. And we represent, well, copper is a metal, but we represent solid things with the S. And then if you go down, 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 you're gonna find zinc. We have zinc 2, and that's gonna give me zinc solid or zinc metal. So I have compound A and I have compound B, and you can check that I'm going down. Therefore, I have a spontaneous reaction. Okay, so I have the spontaneous reaction. Now you might be wondering, okay, but that doesn't answer if zinc goes here or if copper goes there. So what do I do now? Okay, so this is really important, and we're gonna use this later. So you know that I have a spontaneous reaction. Now I need to know if I have what is the reduction and what is the oxidation. What is the reduction part and the oxidation part. So to calculate that, let me erase this first. I'm gonna use these formulas here. Okay, so I have compound A, right? So let's start with that. So my compound A is copper. So I have copper 2 plus, and I need to balance that. Some of you might know this part here. So I have a positive charge. I have a 2 plus charge. So I need to cancel out that to have a 0. So I'm gonna add 2 electrons because this charge is negative. So I have my negative 2 and 2 plus. So that's gonna be 0, and that's gonna give me copper metal or copper solid. Then I'm gonna have my compound B. So as you can see, for part A or compound A, I started with copper 2 plus, and then I ended up with copper solid. What about compound B? So if you check here, compound B is here. It's all the way down. So I'm gonna start here because my arrow ends on zinc. So I'm gonna start with zinc metal. So zinc solid or metal gives me zinc 2 plus, which is this part here, and I need to balance that. So I'm gonna have 2 electrons like that. Okay, so now I need to calculate what is the cathode and which one is the anode. So usually in chemistry we put here the cathode and we put here the anode, which is the negative one, and this one here is the positive one. However, you can change that. That's completely correct. You can change the cathode there, you can put the anode here. That's correct, as long as you have the correct metal or compound here and the correct metal or compound there. So don't worry about that. Okay, so I have this one here. So which one is going to be the anode and which one is going to be the cathode? So I need another part here. So as I said before, I need to find the reduction part and the oxidation part of this equation or of this reaction in general. So I have reduction and I have oxidation. So I'm going to abbreviate that because we don't have a lot of space. Okay, so as I said before, there is a lot of theory behind this, but at least for this part there is a handy tool to find what is reduction and what is oxidation. So you're going to have reduction if your ion, when I say ion, I'm talking about this and this here. So if the charge, so just for example, this is the charge, right? 2 plus and you have 2 plus. So you start with the charge. In that case, you start with 2 plus. So if the charge becomes more negative. So that's the first one. So for reduction, I'm going to have reduction if the charge of my ion becomes more negative. And for oxidation, it's going to be completely the opposite. So if the charge of an ion becomes more positive. Okay, so I have that. Okay, so now I need to find which one is reducing and which one is oxidating. Okay, so I have a charge here, which is 2 plus, and then I have 2 plus here. What about this one? What about this one? Obviously, 2E stands for electron, right? Electron. So that we won't consider that. However, what about this part here? So in chemistry, every time that you have something like this, an element, we consider that as a neutral element. So that's going to have a charge of 0, and that's going to have a charge of 0. So let's take the first equation, the first half equation. So just imagine that you have 2 apples, and you want to go over to, you want to have 0 apples. So in order to go from 2 apples to 0 apples, you have to eat the apples, right? So you are reducing the amount of apples that you had from before. So if you started with 2 apples and now you have 0 apples, you are reducing the amount of apples. So I'm going to have reduction there. And also, since this is just half the reaction of my cell, this is going to be my other half reaction. So if I have a reduction here, I must have an oxidation there. So now I have reduction and I have oxidation. But that doesn't answer where is my cathode and where is my anode. So it could be this one, that could be the anode, that could be the cathode. How do I know that? So, and this is the last step. So this here is really, really handy because there is, as I said before, there is a lot of theory behind this part here. So here's a really neat trick to calculate that or to predict that. So if you take the word cathode and you take the word anode, let's compare the first letter of each word. So I have C and I have A. So I have a vowel and I have a consonant. So if I try to match a consonant with a consonant, that would be cathode, that starts with C, with reduction, that starts with R. And the same for anode. So I have a vowel, I'm gonna compare that with oxidation. And oxidation starts with O. Therefore, now finally I have my answer. So, since copper is reducing, that's my reduction part, copper is gonna be the cathode. And then, since zinc is the part that is oxidating, zinc is gonna be my anode. And now I have everything that I need. So this strip here, since I have anode here, this strip here is gonna be zinc, and that strip there is gonna be copper. As I said before, they are called electrodes, but strips, electrodes, same thing. So I have that, and then I have a multimeter here, and have some solution here. Usually for these solutions here, I add something that is not gonna affect the electrochemical reaction, something that won't react. So let's say that I'm gonna add, obviously you can add different things, but today I'm gonna add a solution with a concentration of 1 molar of zinc nitrate. And in this part here, the same, a solution with a concentration of 1 molar of copper nitrate. So, and here's the really cool part. Okay, so pretty much this is everything. That's everything. But this is really cool. Okay, so I have my anode here and I have my cathode there. So I start with zinc, right? If you take zinc, you see that you are leaving 2 electrodes free. They are not doing anything here. So they are gonna travel from here to here. So now I have 2 free electrons here. So what's gonna happen? Easy.
So since I have two free electrons here, they are going to stick to that copper ion with a charge of 2 plus, and they are going to create copper solid. So if this half reaction is giving me 2 electrons and they are free, they're going to escape from this beaker and they're going to travel through here to this part here. Well, actually they travel here, sorry. So they are going to travel all the way there and they are going to be here. They are going to stick with the copper ions and they are going to create more copper. So let's say that you started with a strip like this that weighs, I don't know, 2 grams. If you let that cell run for let's say 5 hours, so your cell is running for 5 hours, you just leave it there, you're gonna have a strip. So this is copper, right? That weighs, let's say, 6 grams. So you started with 2 grams and now you have 6 grams. Well, at least for me that's really crazy, because just by only transferring electrons from this part to this part, you have more copper. And you might be wondering, okay, but where did that come from? Well, easy. Since this part here has copper, you are taking the electrons over there, you are sticking in with that copper part here, and they are going over there. And that's pretty much everything. So as I said before, this is a galvanic cell. That's how that works. So for our experiment, the voltaic pile, we won't have something like this. However, if you want me to do something like this during an actual workshop at PCC, just leave your comments down below. We're gonna read them, and we can have some cells like this. This is really cool once you have the solutions. All that, obviously I don't have zinc nitrate or copper nitrate at home, but we can do that at PCC. So if you want that, just comment down below. We're gonna read that. Maybe we can have more cells. Maybe we can have the electrolyte cells. We can have 2 or 3 galvanic cells. So yeah. So this is the first step for our experiment. Now we're gonna start with a real experiment. So see you there.
So, as I was explaining a couple seconds ago, copper 2 ions are reduced to copper metal at the copper electrode, which is the cathode to the right. The copper strip gains mass, and the concentration of the copper 2 ion in the copper solution decreases. And that's why we can see all those little tiny particles on the copper strip. Also, this type of cell in theory is providing 1.10 volts of energy, so we should be capable of lining an LED and a small calculator at a time. You can see that over here in this part here. And you will be able to see this more in action later during our actual experiment. So the materials are, we need some pennies and aluminum foil. I'm pretty sure that all of you have some pennies at home, but I don't think all of you have galvanized washers. However, if you do have them, you can use them instead of sanding one side of the penny. That would be faster. We need acetic acid, which is commonly known as vinegar, but we are scientists, dude, so let's call it acetic acid. And we need salt water solution. So you're gonna add 3 to 4 spoons of salt into a cup full of water, and you're gonna mix that, and that's gonna be your salt solution. We need a piece of cardboard of around 40 by 40 centimeters, 1 or 2 LEDs. They are really cheap and you can buy them on Amazon. They cost around 5 to 4 cents, so pretty cheap. We need electrical tape. This is the black tape that people usually use when doing electrical connections and that. We need an electrical sander or sandpaper. You don't need to have the actual electrical sander, but if you do, that would make everything faster. And finally, some containers to pour the vinegar and salt water solution. Some useful information before burning all your house down. Remember that LEDs are polarized. The flat side of the LED, as you can see on the picture, is the cathode, or the negative side, and the long leg is the anode side. So consider this when building your actual voltaic pile. Batteries also have a positive and negative side. As you can see here, the cathode is the positive and the anode is the negative. This is commonly changed when using LEDs. As you can see here, you can compare the two pictures, cathode positive, and then we have positive anode, but that's just for LEDs. So don't get confused with that part. That only happens with LEDs. Remember, our voltaic pile is an actual battery. So the same principles applies here. The zinc side at the top is going to be the negative side, and the copper on the bottom is going to be the positive part. So let's start. So step one, take your pennies and start sanding them. You only need to sand one side of the penny to expose the zinc. If you have an electrical sander, use that because it will be faster. If you don't have that, take 100 grit sandpaper and sand one side of the penny. Step two, cut thin cardboard into pieces just a little bit bigger than the penny, and then put them in some vinegar and put some others into a salt solution that you will prepare. Step 3. Let's start our battery by placing one of the pennies with the copper side down on a piece of aluminum foil. Then place one piece of cardboard on top and continue this process at least 9 times. So you will have a total of 9 pennies. Step 4. Let's use some electrical tape to hold everything in place. And now let's start testing our battery with our LED. To test all the use of your battery, leave your LED together with your battery to see how many hours this can last. Obviously, this is gonna vary. In my case, I can have, for example, 4 hours. You can have 3, 2 hours. That depends on the concentration of your vinegar and also the salt solution. Step number 5. Remember that if you use washers, your zinc washer on the bottom is gonna be the negative part, and the penny on the top is the positive side. Also, when cutting your cardboard, these little pieces shouldn't touch to avoid any short circuit. And then finally, we have step 6. Remember to test both solutions, the salt solution and the vinegar one. So you want to place all your little pieces of cardboard in salt solution and vinegar solution, and then you're going to test both. And then you need to make your own conclusion, and later we're going to discuss all this. So finally, it is time to start. Prepare all your materials and let's go.
Hi everyone, so these are the materials that we are gonna use today. Here I'm gonna add some salt to make a saltwater solution. In this cup, I'm gonna add some vinegar. I'm gonna use gloves for protection when using the electrical sander. An electrical sander, and as I said before, if you don't have one, that's okay, you can use regular sandpaper. And here you have some. Here I have my multimeter that I'm gonna use to compare the voltage and current. These wires here are called probes. Of course, I have here my pennies. My thin cardboard. I'm gonna use some scissors to cut all those little circles, and that's it. I'm going to start by making my salt water solution. Pour about 4 spoons of salt into a cup full of water and mix. Then, in the other cup, I'm gonna add some vinegar. The quantity really doesn't matter because the concentration of acetic acid won't change. Now it is time to draw some circles on your cardboard. You should use a penny as a reference. In total, we need 18 circles, 9 for the vinegar solution and 9 for the saltwater solution.
Once you have your little pieces of cardboard, put 9 in each solution. Wait around 4 to 5 minutes. Now, if you have an electrical sander, you can follow this procedure to remove the copper layer from your pennies. However, if you don't have an electrical sander, that's okay. You can take a sandpaper and start sanding your pennies. This will take a while, but it will work. Just be patient. Okay, so now you should have 18 pennies in total, ready to go. This is the zinc side and the other one is the copper side. So now, take a piece of aluminum foil and place the zinc side of the penny on top of the aluminum. Now, take a piece of cardboard from one of your solutions and put it on top of the penny. I'm gonna start with the acetic acid solution, but you can start with the salt water solution if you want. Be sure to remove the excess of your solution by using paper towel. And repeat this process 9 times. It is time to measure the current and voltage of your cell. The negative wire should touch the aluminum foil and the red one should touch the last penny. Check this out. This cell is providing almost 5 volts. Really crazy, right? Finally, take one LED and let's do some magic. The negative LED goes with the aluminum foil and the positive one with the penny. And there you have. You have created a battery. Now I'm gonna test my salt water solution. As you can see, this cell only provides roughly 3 volts. However, this is more than enough to light an LED. Lastly, I'm gonna compare the values of current for each cell. As you can see, the vinegar cell provides more current than the salt water solution, and the difference is a lot. Now you can make some really cool souvenirs for your friends. Take a piece of electrical tape and tape your LED on your battery. This must be really tight, so each leg of the LED touches each side of your battery. And there you have a really cool and cheap gift for your friends. You can use different colors if you want. So that was the first part of this experiment. Pretty cool, right? Did you ever think that a couple of pennies would be able to light an LED? Science, people. Now it is time to test your other solution. Now that you have tested your first solution, either the acetic acid or the salt solution, let's try your other solution to check if the brightness of your LED is the same. You can try different colors if you want. However, please do not use the red or green LEDs. They consume more voltage than the blue and yellow ones. So what are some differences? For the acetic acid solution, we can see that its voltage was almost twice the value of the saltwater solution. Also, the current of the acetic acid solution was way higher than the salt solution. You can modify these two values for sure by putting more pennies, and for sure you will be able to light something bigger than a simple LED. How long did it last? Well, I'm pretty sure that you won't believe me, but the vinegar solution lasted almost 8 hours, and the LED in the saltwater solution lasted almost 10 hours. This is extremely crazy if you ask me. Who would believe that 9 pennies are capable of lighting an LED for 10 hours? So now you're able to appreciate the real science behind chemistry. Chemistry is not only a lot of numbers and calculations. Of course, they are a fundamental part. However, the real beauty of chemistry lies in all the experiments, predictions, simulations, and calculations that you can do with simple things as a penny, salt, and water. By the way, a little disclaimer here. Did you know that it is a federal crime to destroy or alter currency of the United States? Some people have asked about the legality of treating pennies in this manner. The federal law states that there are exceptions made for use as educational, amusement, novelty, jewelry, and similar purposes, as long as the volumes treated and the nature of the treatment make it clear that such treatment is not intended as a means by which to profit solely from the value of the metal content of the coin. For more information, you can visit that website. Chemistry versus physics. Who would win? So a lot of people say that chemistry is better than physics or that physics is better than chemistry, but what is the truth behind all this? Well, the truth is that both are different branches of science, and each one studies different things. Also, each one derives from calculus. Calculus, as you may know, is the basis of everything in the universe, and everything follows the laws and principles of calculus. So let's compare these two. Chemistry. A study of interaction of the atomic and molecular war. Chemicals make up the universe, and chemistry is what organizes its elegance into a useful and groundbreaking form. The study of change of matter and synthesis lies at the heart of chemistry and gives rise to concepts like organic functional groups and rate laws for chemical reactions. These are extremely important concepts in chemistry. Then we have physics, a study of the actions of the war, how things move, how forces affected the war, in the hidden mathematics of the universe unseen to the eye. Physics is involved with the fundamental principles of physical phenomena and the basic forces of nature and gives insight into the aspects of space and time, dealing with the basic principles that explain matter and energy too. So, what are some of the possible careers that you might choose later in your life? So if you're thinking to become a chemist or study chemistry, here are some: to be a chemical engineer, to be a forensic scientist, a geochemist, we have quality control, we have consulting, and we have more, obviously. Then, if you're thinking about physics, we have data analyst, we have design engineer, we have laser and optical engineer, we have the aspect of robotics, we have geoscience, we have all industry, and then we have some careers that overlaps, like to be a high school professor, to be a lab technician, or to be a research assistant. Obviously, you can be a university professor, but at least for that position, you need a master or a PhD. So, before finishing this workshop, I wanted to show you a really cool and easy experiment that involves a lot of physics, because I know that some of you really like physics. And it will only take you 3 minutes to do, maybe less, who knows. Have you ever heard about implosions? What is an implosion? What is the difference between an implosion and explosion? There are many different ways things can implode. An implosion is simply the opposite of an explosion. In an explosion, matter and energy fly outward, but in an implosion, matter and energy collapse inward. All implosions will need some sort of pressure from the outside, pushing it to cause the object to collapse. So in short, implosions are caused by having a great pressure on the outside of an object. So let us implode something. Not quite like that, but you will the idea with this experiment. You will need some soda cans, you will need water, you will need cold water, and you will need a stove. Please follow the instructions of the video because we're gonna be using really hot water. So just be careful and let's go.
Hi everyone again, so we're gonna start with our second experiment. This is the last experiment for this presentation. As I said before, these are the materials. We're gonna use some soda cans or juice cans, same thing. We're gonna use water. This has to be cold water, so I have this here. This is frozen, so cold water. We're gonna use a stove, so you need fire. And I'm gonna use this thing here. I'm not sure about the name, but yeah, we're gonna use this. So let's start. Bye. So these are all your materials. Take your can and add some water, roughly about 20 milliliters. We don't need a lot of water. Now let's start boiling this water so you can generate some vapor inside your can and therefore some pressure inside your can. Wait about 5 to 6 minutes until your water is boiling. And then put it inside your cold water. And that's it. Okay, so let's try it. Really cool. Now, I have some really neat slow motion videos for you so you can appreciate everything. Okay guys, remember that we are using really hot water, so be careful please.
Okay, everyone, so we're done for today. I hope you enjoyed this workshop. Take care and stay safe at home. See ya.